Okay guys, let's have a look at example 14.4. Remember, we're still looking at the principle of work and energy. Okay, remember the principle of work and energy is that we have an initial kinetic energy and we have a bunch of work due to forces, different forces acting on the particle, and the initial kinetic energy plus any work by any forces done on that particle gives us the final kinetic energy. This is half mv1 squared, and that is half mv2 squared. And recall that if we have problems involving force, velocity, displacement, force, velocity, displacement, we can use this the techniques here of work and energy. Okay? So now, what does this problem say? It says we have a platform P. It has negligible mass and is tied down so that the 0.4 meter long cord, okay, these cords here are 0.4 meters, and it keeps a spring that is 1 meter long. Okay, so let's draw an imaginary spring here. Okay, so the spring is in an unstretched length is 1 meter if you just leave it, but it's compressed 0.6 meters. Okay, so let's redraw this. So here, let's say it's compressed 0.6 meters. So there's the platform, there's that platform P, and then we compress the spring so that it is compressed like that. Okay, and we know that this is 0.4, and then it's got these cables there. Okay, so it is originally 1 meter, it's compressed 0.6 meters down so that the length of the spring is 0.4 meters. So we know that this is 0.6. Okay, and then it's fixed. Okay, so this is a fixed position. Then a 2 kilogram block is placed on top of the platform and pushed down so that this height is 0.3. So it's gone down even further. Oh dear. Okay, it goes down even further. Okay, this is now 0.3, and it's got a brick on it. Okay, so originally 1 meter, compressed so the height is 0.4, compressed even further, so the height is 0.3, and then it is released from rest. Okay, the block is then, this whole system is released from rest. Okay, then it says determine the maximum height h that the block rises in the air measured from the ground. Okay, so we tie it down like this, we put the brick on, we push it down even further, and we let it go. So it has an initial speed here of 0 because it's from rest, and it goes all the way up to a maximum height here. Okay, this height is measured from h. Okay, so what is the question? Determine the maximum height. Okay, so we can use the principle of work and energy. Okay, because we've got velocity information. The speed over there is 0. The speed over there is 0 because it comes to, it turns around. And then we are looking for h, which is position information. And we've got forces. Okay, so we can use the principle of work and energy. Now, remember, the first thing we always do is we draw a free body diagram. Why? Because the second term is the work of all the forces. It is the sum of all the work due to all the forces acting on the brick. So what are all the forces acting on the brick? Sorry, phone rang. I just had to take it off. I need to finish this video. What are all the forces acting on the brick as you let it go? Well, we know that the spring force is going to push it up, and the weight is going to apply a force down. So we have a spring force on the brick. Remember, we're just looking at the brick now. The brick, during this, it's going to move from this 0.3 to 0.4, right? Because that's going to restrict it again. So it's got an upward spring force that wants to push it up, and it's got a downward weight. Okay, there's my free body diagram. It's very important that we do this because we are looking for the work due to all the forces. Okay, so there is the principle of work and energy equation. My T1 and my T2 both have velocity information. So what is my velocity 1? It is 0, so this becomes 0. What is my velocity right at the top? It is 0. So we are left with just the work done. We don't have any initial and final kinetic energies. We just, in order to solve this problem, we're looking at just the work done. Okay. So, now, what is the work due to a spring? Right? This is it. Recall that it's minus a half Ks2 squared minus a half Ks1 squared. Or simply a half Ks1 squared minus a half Ks2 squared. Now the question that I have for you, what do these S's refer to? Are the S's referring to this 0.4? So let's look at S1 now. This is in position 1. Is S referring to 0.4 or 0.6? Okay. Is S just simply the height of the spring? Or is it the compression or the stretch of the spring? That's the question I have for you. What does S refer to? That is the $1 million question. Okay? So what you need to see is that the S refers to how much the spring has been stretched or compressed. So this refers to the stretch or the compression. Okay? How much it's been stretched or compressed. It doesn't refer to the height of the spring. It refers to how much it has been stretched or compressed from its equilibrium position. So its equilibrium position is 1 meter, and it was compressed 0.6 meters at state 1. Okay? So this S1 over here I'm sorry, S2. This is state 2. This is state 2, and that's state 1. Okay? The reason is that it's point 1 or state 1 is when it is compressed so that the height is 0.3. That means S1 is this 0.7. That's how much it was, the spring was compressed. At state 1, it was compressed 0.7 meters. Okay? Then it was released, and it traveled through 0.1 meter until it was at a height of 0.4, and the compression was 0.6. Okay? So that's what we have here. So this S2, okay, is 0.6 because it's the final compression. And S1 is 0.7 because it's the initial compression. And of course K is given as 200. So we just put those in there and we get the work due to the spring. Then we've also got work due to the weight. And we know that the particle is moving up, but the force of the weight is acting down. So this should be a negative. So there's a negative work due to the weight. Okay? So we have the weight, which is just this 19.62. But what we're looking for is this total height. Okay? And what is its delta y? Its delta y will be this here. I've messed it up. There. That is the delta y. That's the initial height, that's its final height. So the delta y over here is going to be h, which is that total height minus the initial height. Okay? So my question now is, I'm just going to ask again conceptually, does the spring do positive or negative work? Right? Remember that if the spring is compressed like that, and it moves, and there's its equilibrium position, and it moves towards the equilibrium position, then the spring force is in that direction, and the displacement is in that direction. So because of the dot product, if they're both in the same direction, we have positive work. And in this case, the spring is moving towards, it's moving from a 0.7 compression to a 0.6 compression. It's moving towards equilibrium, so it should do positive work. That is one way to check if what you've done here is correct. Okay, and we solve and we get height equal to 0.963. The weight is doing negative work because the block is moving up and the force of weight is down. The spring is doing positive work because the spring force is up and the motion is up. Okay, all right, cheers.